Hello everyone, I'm Dr. Mehraei, and today we are going to talk about Monte Carlo methods. You know, we live in a universe full of chaos. Most of the events around us are random. That's why in reality, we define variables mostly as random variables. Even the smallest actions in our world can have huge consequences. However, statisticians study this chaos and try to find paradigm even out of this mess. And that's the reason we will talk about random processes in the following lectures. But first thing first, let's see how we can simulate random number generation. So there are basically different methods of that, and we have, for example, methods using known distributions, and we know that it can be divided into discrete and continuous ones. If you know your distribution, it's pretty easy to generate numbers from them. And when you want to write a program for it, usually by default, they are defined on your program, so that's pretty easy to generate them. And but sometimes we don't know what distribution we should follow. In that case, Monte Carlo methods could be very useful. In case of discrete distributions, or even for continuous distribution that we want to transform into discrete ones, let's see how we can deal with that. If we have a uniform distribution from 0 to 1, we can partition them into fragments like this. Like, for example, if your random number happens to be here in this interval, you can represent it by x1. Again, if it happens to be here, then again you represent it by x1. That's how we dealt with it also in binomial or Poisson distribution. Between 0 and 1, between 1 and 2, we didn't have any points to calculate the probabilities, right? Now, assume that instead of 0 to 1, you can extend it to 0 to infinity, and we have integers here. We can follow the same rule. You see where I'm going with that? So that's the way we can transform your continuous distribution to discrete ones. And I also told you about the approximations, vice versa, that can do for binomial to normal distributions, and so on. For continuous distributions, also, there is a method which you can see here, rejection method. You can study it in the book to see how we can deal with them as well. It's pretty easy comparing to the ones that we talked about, but that one we will talk about it more in the future lectures. But the topic for today is related to Monte Carlo methods. And to know that, we should know about Chebyshev inequality first. In this inequality, you can see it depends on mean and variance of your population and a number which is a positive one. Okay, so look at this slide very carefully, and then after that we can go through Monte Carlo methods. So there are different methods that they follow this approach. Well, what is it exactly? In this approach, we generate many random variables from a distribution and estimate probabilities, means, standard deviations by simulating what happens in the long run. Okay, so there are two important points here. We said distribution, we didn't say which type of distribution. That's the beauty of Monte Carlo method. Because we don't care what distribution follows, we can use this method. And we say by simulating what happens in the long run. It means that manually it's very hard to calculate them. That's why you guys as computer engineers, as programmers, we should find a way, we should type the code the way that we can simulate such methods, Monte Carlo methods, and they are basically stochastic. And we will talk about them later in the future lectures, that how we can really simulate them. So that's our job as computer scientists or computer engineers to deal with that. So that's why it's very important to know about Monte Carlo methods. Okay, so for estimating probabilities in such methods, we should know what we are doing exactly. All right, so we have probability and we want to estimate it. And whenever we want to estimate something, you remember for parameters or statistic, we use this estimate with using hat. So p hat, it means that estimation of p. Okay, so in this probability, we can see we define it like X is an element of this set, what we are talking about here. So in the previous slide, I told you this slide is very important. We can see that each one of these fragments can be defined as a set. And even the union of them as a universal set, it can also cover A as well. So whenever we define sets, we can show them like fragments like this as well. But we talk about the number of them. See, number of x1 and so on until xn. What is this n here? The capital N here stands for the size of the Monte Carlo experiment. As soon as you understand about this part, we should know how accurate is such method. So here you can see this probability should be less than or equal to the significant level. So you define this based on the significant level. That's nice. It's like constructing a confidence interval. So now everything looks much better as soon as you have this significant level. So at the end, you can report this is, for example, 95% accurate. This is 99% accurate. So it happens based on the significant level again. And this is a famous question to ask: how many runs we should have for our stochastic experience, and how many, what should be the size of our Monte Carlo experiment. In that case, you can follow this formula. I know scientists don't have common voice about it, but honestly, it depends on the topic and the problem. However, if you want to stay in the safe zone, use this formula, and you can find the proof also in the book about both of these formulas. And by the way, don't listen to this cat. What is chaotic is actually the grammar in the sentences. But as I said, statisticians are doing their best to model even the most chaotic events using probabilistic methods. So everything is under control. There's no room for panic attack. And as you know, out of this chaos in the universe, we have the planet Earth, and we are alive. Think about it a little. See you guys.